the end of the world. All right, so we now come back to finish the linear algebra story, and I will make an effort to tie it in with the calculus we've been doing to some small degree. I can't tie everything in, but I will try to show you some ways that the linear algebra we're doing ties in with the stuff we've done in Chapter 8. It's sort of cool, actually. So what we want to do here is basically arrive at a better understanding of linear maps, and I'm going to, for reasons of expedience at this point, I'm going to say we're going to study for the rest of the course just linear maps from Rn to Rn, or square matrices. And the basic question is, if I write down an n by n matrix, likelihood is that you're not going to recognize from this matrix what the linear map means. But suppose I told you that a 3 by 3 matrix represented projection on some two-dimensional plane. You actually figured out at the end of last semester, you guys figured out how to give matrices that do projections onto subspaces. You don't remember how you did that, but you did it. You had two ways of doing it, actually. Suppose I even told you, here's this 3 by 3 matrix, it represents projection on some two-dimensional plane. How would you find the two-dimensional plane? How would you convince yourself it's correct? Okay, you could look at the column space and it would be a two-dimensional plane. How would you decide that in fact it really is projection on that two-dimensional plane? What would you have to find? So here, the question I'm posing here is, if T, mapping Rn to Rn, represents projection on or reflection across, I'm just giving you examples here, a k-dimensional subspace V. How do we know? How can we tell? How can we find V? How would we know this?
Could we feed it the standard basis factors?
And then what? And how would we find V? So Cameron has already suggested, at least in the projection case, if you looked at the column space of your matrix, that would tell you where all the vectors were landing, and so if you were really projecting on a subspace, the column space would tell you what the subspace is. But if I'm doing reflection across a plane, that ain't going to work. So what characterizes projection and or reflection geometrically? Suppose, just to make life simple, that our subspace were sort of sitting there in a flat way and you recognized it was like the xy plane here in R3, something simple. How would you recognize projection or reflection geometrically?
Well, projection, the z coordinate would go to 0. And reflection, it would be
Okay. Can you give me a statement in terms of a basis chosen in a clever way for Rn? Okay, so start off with V1 to Vk. They give you a basis for your subspace. What do you mean the rest? Well, do I want to do it in any random way? If I took a random vector like this and I projected, that's not very helpful.
Cross and
Well, what if I'm in more dimensions, Patrick? But you're on the right track here.
Use a basis for Rn that includes those vectors.
Yeah. I'm looking for n minus k more vectors to make my complete basis. How do I want to pick these guys?
All orthogonal, all outside V. All
No?
orthogonal.
Orthogonal. So
In V
they should
perp.
form a basis for V perp. If your remaining vectors are in V perp, then what is the linear map going to look like in terms of this basis? If you're doing a projection, what happens to this basis?
It shrinks to the red ones.
Give me a more precise statement.
The negative.
No, wait, I'm doing projection. If T is projection on V, then what happens to these guys?
The part of
They stay the
VJ.
same.
They stay the same. So the V's stay the same if you're in the red range here, and they vanish if you're in the perp range. Does everybody agree with that? And what if T is reflection across V? So V is like a mirror. What's T of Vj going to be now?
Vj
It is
is
the
1
same.
less than j,
It's
same
negative.
plane, negative Vj.
So the ones that are in the plane, the red vectors, again, stay identical to what they were, but the ones that are orthogonal to V switch to the negatives. So what you're really going to want to ask yourself is, if I give you a square n by n matrix, can you find such vectors? How would you go hunting for such vectors that have these properties? And if it's a general linear map, what's analogous to this?
Well, for V, could we use basis vectors in column space?
Okay.
And then for B, what's the...
Well, that again, that would work for this case, but not for this case.
Okay.
So what I want to say is, what I'm hinting around here is, given a linear map, is there an optimal coordinate system in which to understand the linear map? Is there a conveniently chosen basis with respect to which the linear map becomes clear? So the magic word, Llama just intoned here, eigenvectors. What we're looking for is vectors that don't change direction when you apply the linear map T. Now, before I get to, so I'm actually going to start in on that on Friday, but what I want to talk about today is how do we, all you know about so far is the standard matrix for T. Remember that from chapter 1 and chapter 4? So this was the standard matrix for T, and how did we make that matrix? How do we make the standard matrix of T?
You took, for the first column, you took T of E1, then T of E2.
Right, so you took the standard basis vectors, you applied the linear map, and you said to yourself,
So,
what is T of my standard basis vector? Put it in as a column, etc. And what I'm suggesting now is that if I take a different basis, then I want a different matrix representation that's all in terms of that new basis, which is going to be more convenient. So, given I'm going to say an ordered basis, just to be pedantic, I want to make sure that you keep the basis vectors not just as a set, but in a particular order. So you know which one's first, which one's second. Just like the standard basis, we put it in a standard order. So I want to have an ordered basis. I'm going to call that script B. I want to define the matrix representation of T with respect to that new basis. So like, for example, if we were looking at these examples here, what do you think would be a matrix representation that encodes this information? just thinking in your whole world is just the v's. You don't have any other coordinates.
Just do the same
Yeah,
thing.
that V1 instead of
So what should the first column be?
T of V.
T of V1.
What is t of v1?
V1.
So I want to say it's 1 v1 plus none of the others. So I'm writing everything now in terms of my basis vectors.
So for the first K column, you're gonna have a 1 in the K slot, and then you have zeros everywhere else.
Yep. And if I were doing the reflection matrix, what would it be?
The first K columns look the same, and then the second, and then the final columns have negatives.
Negative.
After K columns.
So would you agree it would look like that? This is a little k by k identity matrix, and a little n minus k by n minus k identity matrix there. So clearly, if someone hands you these matrices and says, this is representing a linear map in some basis, you say, oh, I know exactly what the linear map's doing.
Can we?
So let me give you the definition, just encoding what I just said here, and then we're going to figure out, okay, how do we relate matrices in two different bases? So we're going to define this to be the matrix whose columns are T of the various V's, but written in terms of the basis of V's, not in terms of the standard basis. Expressed in the coordinates of the basis B. So we talked about this back in chapter 4, but you've probably forgotten. If I have a basis for a subspace, then I can represent any vector in that subspace in terms of a linear combination of that basis, and I can have coordinates with respect to that basis.
Which is really what you're doing in a given standard basis.
Yes, that's exactly right. So in other words, I'm going to say in this case that the matrix of T with respect to the basis B is a matrix A, where if I want to know what T of Vj is, that's going to tell me the jth column of A as linear combinations of the basis vectors v1 to vn. So do you understand that that's this formula? Jth column of A, and then you take the first entry in that jth column times the first vector, second one times second vector, third one times third vector, etc. So this is a formal way of writing down that the jth column of this matrix is given by the coordinates of T of Vj in the basis v1 to vn. Are you guys lost, or are you okay? So it's what you're used to doing, what Daniel recalled here, except now we're doing it for the v's, and we're staying consistent. We're doing it all in the v coordinate system. So you don't want to be doing stuff like doing part of your integral in Cartesian coordinates and part of it in spherical coordinates. Everything has to be in one coordinate system. Just here, everything's now in the basis that we're working with. So my question to you guys is, how do we go back and forth? If you know the standard matrix, how do you find the matrix with respect to a different basis, and vice versa?
Do we know the basis?
Yes. So if I give you a new basis, so the book is going to do this slightly differently, but I think I'm going to do it the way I think that ought to be slightly easier. So I'm going to say, given the standard basis, say, strip B, and a new basis, say B prime, how do we relate the matrices with respect to the two different bases? So in the book, I'm not always thinking of the standard one as being B. But you can always, if it makes, I think it's easier to think of it this way, and then you can always adapt yourself later. So exactly the question that Ken just asked is, do I know the new basis? So I'm going to still use the notation that's, I'm going to be consistent with the notation here. So I'm going to say that script B is given by V's. Okay, so perhaps the standard basis. And script B prime is given by V with primes on them.
So would one way be to convert back to the standard basis and then convert again?
Mm-hmm. That's what we're going to do basically.
So just make sure.
But you don't want to do 6 pages of solving linear equations. You want to have a nice matrix way of doing
So
this.
matrix multiplication.
Yeah. So how do we know the new basis in terms of the old? So I'm gonna think of this as new and this is old, but you don't have to do it that way. You can, whatever way you're happy thinking about it. So I want to give, first of all, the new basis in terms of the old. So I'm going to start with what I'm going to call the change of basis matrix. Which tells me how do I give the new basis vectors in terms of the old. So how am I going to make P? Well, I'm going to think of it this way. I'm going to again use columns. That's what we always do. And what do you think the jth column of P is going to be?
So what do we feed to P and what do we want to come out?
So what I want P to do is encode the new basis vectors in terms of the old. So it's change of basis. I'm going from old to new. So what you're going to do is say, what are the coordinates of Vj prime, the new jth basis vector, in terms of the original basis vectors?
This isn't always have to be possible, can it?
Yes. That's what basis means. You can write every vector uniquely as a linear combination. So this is, I'm doing basis for Rn here, basis for Rn here.
Oh, okay.
Same
Like
Rn.
basis for a substance.
No, same Rn. So for example, suppose we're in R2, and I want to take the vector, let's say that's on the 45-degree line. So that'll be, this will be my V1 prime, and my V2 prime will be a unit vector orthogonal to it. And my original V's are going to be the standard basis vectors. Then what would the change of basis matrix be? No, not projection. Yeah, so sorry about this. P is not standing for projection. P is standing for
Right.
change of basis. For reasons, historically, people like to use P's for this. I
Would
don't.
it be like 1, 1, negative 1, 1? Those are columns.
Okay. That seems to be the picture I've drawn. Now, somebody mumbled rotation. You mumbled rotation? So my picture would not be correct for a rotation if I wanted to do a rotated basis rather than what I wrote down, what should I do differently?
The green would be shorter.
The green should be shorter by a factor of root 2, right? So if you wanted to, you could take 1 over root 2 times this matrix, and that would be the matrix you would get by rotating the basis rather than just taking 1, 1, negative 1. I'm fine with it either way.
They're pretty much the same basis, just vectors.
Well, but it's that lengths are going to matter when you write down the ultimate matrix for a linear map. It's going to matter how long your basis vectors are. So it matters. So my V1 prime in the second case would be the blue one that goes like this, right there where they're shorter. Okay. So if that's what... Okay, so I want to introduce one more bit of notation, and then we're going to figure out the formula. If B is a basis for Rn, and X is a vector in Rn, let's say V is a vector in Rn, then I can talk about the coordinates of V with respect to the basis B. Right? Those would be the coordinates. So I would have a vector x, which is the coordinate vector of V with respect to this basis. But I don't want to write all that out, and you certainly don't want to write all that out every time. So I want some notation for this. I'm going to write it as script C, subscript B. So if you want to write a regular C for your notes, I don't care, of V. Coordinates of V with respect to basis B. Okay, I'm going to use this today, and then we're probably not going to keep using it.
Is that A?
No.
In the top row?
No. That's representing the linear map. So I'm not at the linear map yet. All I'm talking about now is just vectors and the basis. So for example, in this example here, e.g., in our example, suppose I took the vector V to be 3, 3. Well, that's the coordinates in the standard original basis. Right? So this would be my coordinate vector in the standard basis.
Wouldn't it be 1, 1?
No, this is a new. You just made this
Oh,
one.
okay.
No. So here's my vector I'm looking at. This is V,
Okay.
which is in the standard basis 3, 3. What is its coordinate vector in the prime basis?
3, 0.
There you go. It's 3 of these guys plus none of those. Okay.
Is that E of B right there?
We don't have any linear maps yet. All I've done so far is coordinates with respect to a basis. Now I'm going to put in matrices of linear maps. So all I've done so far, all I've done so far is say, if you have two bases, say the old and the new, you talk about the change of basis matrix, which goes from old to new. Tells you how to write the new vectors in terms of the old.
Is a P same as A?
No. Now I want to take a linear map.
So it's
And I want to talk about how do I write down its matrix in the B basis, how do I write down its matrix in the B prime basis, how are they related?
this P move vectors from one basis. Is P of B what is P?
Well, so, alright, so, how does P relate to these coordinates?
Are its column vectors, though?
So if I start with a vector in the old coordinate system, how do I give the coordinates in the new coordinate system in terms of the change of basis matrix? So, given x, which is the coordinate vector, now I'm not using the script, of V in the basis script B, and x prime, which is the coordinates in the script B prime coordinate system, how does P relate x and x prime. So I give you a hint, multiple choice. X prime is p times x, or x is p times x prime. You have a 50-50 chance.
I'm gonna be wrong.
The first seems more intuitive, but I'm pretty sure.
Well,
it's
if
the
we
second.
plug- If we plug in the V1.
You really give us the right answer
add
first.
P to get the other.
I think x prime equals p inverse of x.
Can I go on behind the red door?
Combination of both of the columns P.
You're voting for 2?
Well, the first
Number
one,
2.
doesn't the
I
first
mean,
one
if
change?
you apply the P you have
change
and
old
the P
into
you
new?
have, it's not.
The first
Yeah,
one.
that's what we did.
You do have a numerical example on the board.
Yeah.
When you plug in when you plug in the first V1 to your P there, you get V prime 1.
Yeah, I guess the second one works really
When you plug
Cameron, are you talking about the example?
no, I'm going back to this one over here with the red and the blue screen.
Yeah.
Okay, yeah, I'm going to the example.
I think if you try this example, think about what you're saying here. You're saying V can be written as how many V1 primes plus how many V2 primes. And then you say those in turn are given by writing out the P matrix. This would be V1 prime, this would be V2 prime. So if I want 3 of these plus 0 of these, I'm going to multiply this matrix times 3, 0. And when I do that, I get 3, 3. So in other words, this is my x prime vector, and this is my x vector. So I think the people that voted for this equation probably are right.
Weren't you taught not to write anything wrong on the board?
Why do you not forget anything? It was multiple choice.
Why don't we give us multiple choice questions?
You guys want a multiple choice final?
No.
No.
Actually, if it's the same difficulty, like the same questions, just with 4 options,
No, I'll take my partial credit where I can get it.
There are more questions on it.
Could we have multiple choice on the proofs?
Like a fill in the blank.
Just give us a word bank. Word bank, please.
All right, so what's the proof that we see in the example that that's the right formula, but the proof isn't much harder. If you want to take the vector v and you want to write it as x1 times v1 plus and so on, and you also have it written with the primed basis vectors, notice that in terms of matrices, if I take the P matrix and I multiply it by the primed x's, remember the interpretation of this, that I'm taking exactly x1 prime times the first column of P plus x2 prime times the second column of P, and so on. Right? That's how I first defined matrix times vectors, linear combination of columns. But the first column of P, we said, was how you write V1 prime as a combination of the V's. So this is going to be x1 prime times P1 there and J there times the V. So the first column of P represents V1 prime. This is really V1 prime. And V1 prime is this combination. So let's write it this way and say it officially. So therefore, V is the sum of the primed guys times the primed vectors. And what we've said here is that Vj prime is given by the jth column of the P matrix. So this is the jth column of the P matrix, saying that Vj prime is the jth column times the corresponding V's. And now I'm summing on J here. So I now have a sum of Pij xj prime multiplying Vi. So what have I done? I've switched the sum order here. I've done this to you before. Just multiplying these times these, adding them up, saying that's the coefficient of Vi. Well, then that's what xi is, because by definition the coefficient of Vi is xi. So what does this equation say? This says you get the vector of x's by multiplying the matrix of p's times the vector of x primes. Okay? The ith x you get by going across the ith row here and taking the dot product with the x prime vector. So this is the formula that says formula 2. All right. Now you guys have been waiting for the matrices of linear map. So here you go. I'm not going to put the multiple choice question down. But I want to relate the matrix that I start with in the old basis and the matrix that I get in the new basis, which we'll call A prime. So what should the matrix mean? Well, if I'm working in the original basis, if I take T of V and call that W, that should correspond to saying that if I take the coordinates of V in this basis and multiply them by X, I should get the coordinate vector for W. So X is going to be the coordinate vector of V.
Where is the y coming from?
And the Y is going to be the coordinate vector of W. So all I'm saying is you have a linear map that as an abstract function is sending one vector to where it goes. When you switch to matrices and vectors, you're saying I'm taking AX equal to Y. Y is the coordinates of W, X is the coordinates of V. And A is the matrix representation of T. So this is a dictionary that goes from thinking of abstract vectors to coordinates. This is what a matrix representation means. If you think back to what we did way back in chapter 1, we were saying multiplying the matrix by the coordinates of your vector tells you where that vector gets sent by the linear map. That's this equation. All right, so let's just start substituting. I've got X is P times X prime. So Y is AX. Now let's rewrite these in terms of the prime guys. Y is PY prime. And AX is A times PX prime. Well, then surely if these are equal and these are equal and these are equal, these should be equal. So what's Y prime?
P inverse A.
P inverse A.
played before last semester, didn't we? I thought we called that matrix something special, like that combination.
This one looks
Yeah,
like
projection.
Ted's
Or
favorite.
no,
Have you seen this formula before?
Well, sort of, when we were doing
It looks like
the normal equation.
No, 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 that had transposes in it.
No, I feel like we got there.
Yeah,
once
we
before
were doing
called
it with
the
transposes.
Now, you've not seen this before, although you had a homework problem at the very beginning, like week 2 or week 3 of fall semester, where this was lurking, and I'm going to remind you of that. So this is the change of basis formula. This is A prime x prime, so this is the A prime matrix. So this is saying change of basis formula. Then you take the matrix in the new basis. It's given by P inverse matrix in the old basis times P, where P is the change of basis from B to E prime. And if you know, notice the neat thing, if you go back to our original example, which I erased here, where you knew in the new basis that you had a projection matrix that just looked like identity 0, 0, 0, that would tell you this. And so you could use this equation to solve for what the standard matrix is. So I'm going to do that for you in a second. Now, I don't know if this is going to amuse you or not. This formula can be made very nicely pictorially. I'm not sure you'll like this or not, but before I do the numerical examples, here's what's going on. You've got T mapping Rn to Rn. Right? But you've got one coordinate system, the basis B, and in the B coordinates, so in the B coordinates, you're taking vectors and giving them their x coordinates. And then this matrix is what? That was what we were calling A, right?
Yeah.
Yeah.
Right? In the original basis, this was our matrix A. But then along comes our primed basis. Along comes our primed basis. And in the new basis, you've got our matrix A prime. How are these two matrices related? So this is where X lives, and this is where X prime lives. Well, clearly I can draw in arrows here. And P is there somewhere, right? So you now have a diagram here, which is really a three-dimensional picture that relates A prime and A. And what's the formula supposed to be? A prime is supposed to be P inverse AP. So to do A prime, I do this. I come down here, do A, come back here, and so exactly as Ken surmised, this brown arrow is P. X prime,
Would it be the
uh-oh,
It'd be the other way, right? Because P of X
uh-oh.
equals X.
I said it wrong when I did P inverse AP. Yeah, it's going the wrong way. I knew I'd get it. Rewind tape. Yeah. So, what's A prime? First you do P, then you do A, then you do P inverse. Remember, we right to left. And this is consistent because P takes X prime and gives you X. Right? X prime is going to X. And that's exactly what we had. So this is the diagram that says when you switch coordinates from the red coordinate system to the green coordinate system, you've got the brown change of basis matrix that ties it all together. So if you don't want to remember what we did today, you just remember this picture. All right. So where did you see this before? You might recall that back in chapter 1, I asked you to figure out the matrix for reflecting across the line at angle theta. Remember doing that? You chased through where the standard basis vectors went?
Yeah. Oh,
And then I asked you to check that some matrix product formula held. And the matrix product formula was saying the following. To figure out the matrix for the standard basis, let's take that formula. So let's let B be the standard basis. And let's let B prime be the tilted basis that's at angle theta here. What is the formula there? The standard thing is given by P times the tilted representation times P inverse. So my advice to you here is remember this formula. You really do need to just memorize, or else you're going to get confused trying to think through it every time. New one is P inverse old P. But now using that I can solve for the original one, the old basis representation. And then you got the P and the P inverse on the opposite sides. Here's what it's saying. What is T in the new basis? In the tilted basis, if I reflect across this line, where does V1 prime go?
Stays the same.
So there's a 1, 0. Where does V2 prime go? Negates. So what we're saying here is, the way you figure out the matrix in the tilted basis is, you take the easy matrix and you put a P on one side and a P inverse on the other. Haley should be sitting here saying she's been doing this for months in Math 4010. What they may or may not have told you in Math 4010 is, this formula is coming from change of basis. Here's what it means. Start with a vector. Rotate the plane by P inverse. P, remember, rotated the plane to here. So P inverse rotates back. So take the plane, rotate it to make the line horizontal. Reflect, rotate back. And that's exactly the formula you guys checked in that homework problem back in chapter 1, section 4. But this is what's going on geometrically in that change of basis formula. It's just saying, look, we understand it in the red coordinates. Let's make the red coordinates be in the standard position, do the standard thing you would do if you were in the red coordinate system, and then rotate back. Now you're back in your original unrotated coordinate system. So that's what this formula is about. You got a question? Okay. So you're going to have some web work problems to play with. I'm going to do another example. Suppose I take the plane x1 plus 2x2 minus x3 equals 0 in R3. Suppose I wanted to do projection reflection with that plane. How would I pick a convenient basis? So what do I mean by convenient? Well, I mean a basis that's adapted to the geometry thinking about this plane.
Take the normal from one.
Top line and 1 with 5.
Okay, so I'm going to take V1 and V2 primes in the plane, and V3 prime, well, it's easier than that,
Or
just
just
in the
normal.
plane. I mean, perpendicular to the plane. So let's do it. What's the change of basis matrix? Give me a vector that's in the plane.
0, 0, 0.
That can span something.
Alright, 1, or 0, 1, 2.
Give me another vector that's in the plane.
1,
2 and 0.
1.
Now give me the vector perpendicular to the plane.
1, 2, negative 1.
Right? Read it off from the equation of the plane. Okay? Easy. Now you get to use all your fancy ways to do P inverse. You probably don't want to do it by row operations, or maybe you do. Or maybe you're going to just cheat on WebWork and use calculators, or Wolfram Alpha. But you have multiple ways of finding P inverse. You can do the multi-augmented matrix, but we call that super-augmented matrix with the identity. Or you can do cofactors. And with a 3x3, cofactors is actually faster, I think. And if you do it, I actually did do this. P inverse is this. There's P inverse.
Do we happen to use the exact same one you did?
Hmm?
Do we happen to say the exact same P that you used?
Well, I changed it so that it was, right? I moved that to the second column.
We could have said like,
All right, so what's the standard matrix for projection on this subspace V? Well, what's the matrix in the convenient basis? You guys have told me this at the beginning of class. What happens to the prime basis vectors?
That's
One.
state segment.
All right. And if I were doing reflection, I'd have a -1 there. But then look how cool this is. It follows by the same thing I wrote down here, that if you want the standard matrix, you just do P times the convenient matrix times V prime. So the standard matrix is P times the convenient matrix times the inverse. And if we had another few minutes to do the arithmetic, we could multiply this out, as you will do on WebWork, perhaps with the assistance of technology, and we would get a matrix that would have been what you would have gotten if you had done it the way we were doing stuff in Chapter 5 at the end of last semester, in terms of the normal equations, or Gram-Schmidt, or however you wanted to do it back then. But I mean, so the whole idea here, in keeping with what we were doing with integrals, is pick a convenient coordinate system where you know what you're doing, and use the change of basis formula to therefore get it in the less convenient coordinate system. What we'll figure out tomorrow, Friday, is how do we find the convenient basis if we start with a matrix in the standard coordinate system and we want to understand it. How do we decide what the convenient basis should be? So we'll pick up with that on Friday.
Is the web